I'm back up, and let's start sharing some screens here. We're almost done because this week is on equilibrium, and I can't say it's heavy. I got like 50 slides, and it's the math. I've been going through it there the past week, and I was going to try and have something on a whiteboard, but I think I've got it because there's a sequence to do all of these questions. You need to know how to set it up, and hopefully the objectives have been met. So we have equilibrium there this week. This one's a bit of a doozy. Next week it's on gases, and they're actually not too bad. Next week isn't bad at all. It's kind of this. It's not bad. It's not as bad as this week. And then week 6, there's nothing. It's review. I have review PowerPoint. Like, it's just questions with answers. I even have a review package. Like right now, it's at 21 pages that I generally get. I give to my 1009 students, and it's just hundreds and hundreds of multiple choice questions and answers, these kinds of things. So I'm working on this right now. So just know that you can actually see the light on the end of the tunnel. It's only week 4, but after this week, we only have one more lecture left. We have week 6, which is just review, and then week 7 is the test. There is no lecture. So we're almost there. And I understand, I've been getting emails, and I totally understand you guys some of you are feeling all this, and it's perfectly normal. Just keep at it. I think that there was a question, and I didn't see it. I don't know. I can see it when I stop.
Ian?
Oh, hi. That's a lot easier. Go ahead.
I just have a question. There's 2 questions in the chat, but I have a question regarding the lab and then the assignment. What does the assignment do? Because some people are saying it's due on the 16th, but the assignment itself says it's due on the 25th.
Yeah, you got 2 weeks. So I don't know if someone can tell me where it says the 16th.
I think it says that in the on the My Grades.
Oh yeah, yeah. That's from another Blackboard shell. That's I don't even, and they still haven't cleaned that off yet.
Okay.
No. Thank you for that. I'm gonna write that down. Clean. Was it My Grades, right?
Yeah.
This is a problem about importing like a Blackboard shell. Like once teachers make the shells with all of the material in them, they can actually save them, and then next semester, it's already there, right? Well, the dates change and semesters change, so okay, I appreciate that. I will have that cleaned off there by the end of the week. Yeah, assignments, generally quizzes, you have 1 week. I gave you guys 2 weeks there last time, just because it not a big deal at all. But the assignments are 2 weeks. The labs are 1 week. But yeah, you had a question there about the lab.
Yeah, so for lab 2, I'm still very confused on how we get started to find our initial and our final. The video doesn't really show it, or if I'm missing a part in the video and you could let me know. I know a few other students have had this.
There's a chart in the video, looks exactly the same as what is posted there.
So just follow the chart.
That's it.
Okay.
That's it.
Okay, thank you. And then I know 2 people had a question in the chat. Someone asked, will we be able to backtrack in the quiz? And then another person asked for assignment 1, how do they get the bubble sheet?
Bubble sheet is should be assignment 1. There is no bubble sheet. Assignment 1, right here. I can't see it. There we go. Chemistry. And assignment. And you'll see you go into assignment 1. You can print off the paper copy. Okay, I have PDF and Word. And because I know some people like Word, some people like PDF. So this is how you would print this off like now, if you haven't already. Yeah. And what we want to do is you work on this there. Sorry, I was just checking my calendars there just to make sure. Yeah, this has been out a week. So I'm also dealing with 2 different schedules. I have Lakehead schedule, which is 1 week before you guys and all this. So I was just looking at that, and if I thought I looked confused, I actually was confused. And crazy semester. But what I want you guys to do is print off the assignment. Okay? And so you got a paper copy if you can. If you don't, okay, fine. And then once you have your answers, this is a test. This is how you enter your answers. You're not gonna, there's no bubble sheet anymore. There was too much trouble there for the bubble sheet. And so that's how I want you guys to do this assignment. You could actually just go and do the assignment right here, right now. You don't need to print off the paper. If you just want to do it 1 question at a time like a normal test, it's all good. That's how you do this one here. Is that okay? Anyone who had the question? I hope it's okay. This is where you enter the answers. If you want a piece of paper that you guys want to calculate stuff on, this is where you could print this off. But this is just like a test or a quiz, okay? And that's where you'd enter your answers. And I figure there that was a little easier. It's kind of self-contained under assignment 1. You'll see there quiz 2. It'll be the same way. There will be a paper copy there that you can print off if you want, or the quiz is just there. You can stop it and start it. You should be able to go back to any question. I've left it completely open, so it's just kind of like an assignment, which is what a quiz should be. I don't like timed quizzes or assignments because you need time to develop your thought. We got to do timed tests, but that's okay. Good questions, though. How we doing? I am aware of the material from last week. Aha! Last week's stuff. Good. What questions you got? We had a good tutorial there yesterday, and I think we only had a couple of people. Like, as far as I'm just, today's lecture is pretty heavy. So I'm going to be hard pressed to finish this in 2.5 hours. Okay. If you guys have questions about, last week's stuff and all these kind of stuff, I love it. But come to the tutorial that is going on, and or stick around to the end if I have enough oxygen left. Okay. But now we're into, this is it. Everything you've ever learned in chemistry there at Georgian right now, bang. I'm going to ask you to be able to recall it there for today's stuff. And it's not, as long as you guys got half a grasp of what's going on, which I know all of you have more than, you guys are good to go already. Even though, and I need to say this, I need to interrupt myself and say, I don't know why, but a lot of you guys do not believe in yourselves. And I'm being serious, and I don't know why. People have emailed me and they say, I have no idea what's going on, and I've done this and I've done this. And yeah, you've got the right answer. You've done great. There was a mistake in the back of the book or something like this. So you guys are doing great. Keep going. And thank you guys for coming. Welcome to, this is a good one. And everything that we've done so far is for today's lecture. And if you guys have questions there about acids and bases and these kinds of things, we're going to go back into it there today. All right, I've designed these so that there's this interrelatedness amongst the lectures. So do you guys have any immediate concerns? Are we okay? If there's anything that, I'll be around here afterwards. I don't have anything after. So if there's questions there that need to be asked, ask away. I do want to show you something there that this is from my own stuff that I included. And I made this there for, I was teaching in Saudi Arabia there for the Aramco, the world's biggest oil company. And I designed this there for my students there. And I just thought that maybe it would help you guys. Maybe it won't. I don't know. I think week 1, I included a periodic table that you guys could print off. I made this here that, you know, it has the first 20 elements: hydrogen 1, helium 2, lithium, beryllium, boron, carbon, nitrogen, all the way down to calcium. That's the first 20. That's generally where 95% of the things I'm going to throw at you come from. Okay? Like carbohydrates are carbon, oxygen, hydrogen. You know, all these kinds. So everything, most, and what regular chemistry comes from the first 20. Things get kind of hairy and crazy down here. All right? And, but what is most important? And some people there, they've talked to me there, and, you know, they're saying there the last semester there, they didn't get a good grasp as they could have. Well, you know what? It's all good. It's all good. You guys are going to be just fine. And I'm going to show you what this little periodic table can do. You know, sodium sulfide. Okay? You know, when you're making an ionic compound, like I'll give you the name of a compound and ask you to make the chemical equation, which means you got to make this guy, this guy, this guy, this guy. Make sure all the little subscripts are all right. Okay, it's +2 over here, -2. Okay. Oxidation numbers. What I've done is, like, I've given you guys the names. You guys will know these are your alkaline metals, your alkaline earth. You got your halogens, noble gases over here. Little bits and bobs of information, like from column 1 all the way to over here. These are your metals, and they extend down. Here are your metalloids. This is all last semester. These are your non-metals. But what's really important here is these oxidation numbers. I don't know if you guys have them written somewhere or not. But all of these guys here, remember hydrogen should be over here because it's a non-metal, but it's +1. All these guys here are +1. These guys here are all +2. +3. And carbon, don't worry about carbon right now. Carbon is, we say it's +4, but things are going to change there in 4 weeks when we do organic chemistry. Okay? Nitrogen, -3, and there's phosphorus as well. So everything in that column, -3. Oxygen, sulfur, -2. The halogens are all -1, and the nobles there are all 0. So when you're trying to make your compounds, and you got to do the crossover. You guys know what I'm talking about, right? You know, you got +2 here, negative crossover here, and all this. This one here is really, really handy for that. So, like, you'll see there on the quiz and all this kind of stuff where I'll give you the English, blah, 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 and then from that, you will have to make your chemical equation. And in your chemical equation, there could be 4 beasts. Sodium, hydrochloric acid, sodium hydroxide. You've got to be able to make these compounds and make them correctly. I think that there was some questions on last week's assignment, or not the assignment, but just questions I threw at the end that, you know, how to name acids. Like, if there's a hydro in front of it, that means that there's 2. Like a hydrochloric acid, it's just H and chlorine. Hydrosulfuric acid, again, is just 2 atoms, hydrogen and sulfur. I want you guys to to try these out. There's lots of questions there at the end of each chapter there that help with naming. And if you need help with naming and crossing over and these kinds of things, I have all sorts of stuff like that. Formulas. It carries through. We're now into week 4. These are the formulas there we're going to be doing there today. Today we're doing K. Last week we started it. K of water. All right. And that was this one right here. And whatever your hydrogen concentration is, in molarity. Square brackets is molarity. You multiply that by the hydroxide concentration in the same solution, because in a solution, doesn't matter if it's pH 7 or not, you've still got hydrogen and you've still got hydroxide in there, because water, H2O, what was that word again? Self auto-ionization? The hydrogens jump all over the place. So there is this natural phenomenon going on here. So this is the first K value that I've introduced you to. K means equilibrium. Something is going on, and today we're going to expand upon that. pH, just to let you know, know that one, inside and out. Know how to use this one, inside and out. And by the way, these are the same formula, just one is written for pH, and this one here is written for hydrogen concentration. Same formula for these two. So know those two. And know this one. Okay. This one here, I might throw one question on there, or something like this. I don't think this one though. But this one here, just so that you're familiar that there's a pH scale and a pOH scale. And if you add them up, here, if you multiply them up, you'll always get this number. If you add them up, you'll always get this number. So this formula and this formula are actually related. But anyway, if you guys got nothing, I got nothing, we got to move. Okay? There is some animation at the end, and I put that in there painstakingly. But chemical equilibrium. Like if you look at these saltwater fish, one of my friends there, he was a Canadian guy who went down to USC for school. He's a teacher over there, and his thing is he likes to go to exotic places and get strange fish. And he'd be gone for 3 weeks at a time into the middle of Africa, into this isolated lake in the middle of nowhere, and grab a fish. And he would bring it back. And there are some strange fish out there that require a specific pH, all these kinds of things. So there has to be a balance. Now, when I say a balance, we tend to think of 50-50, right? But homeostasis doesn't work like this. Chemical equilibriums don't work like this. This could be your equilibrium, and it's happy like this. Things move, and we'll get into what equilibrium really is. The whole idea of a reversible reaction, rates of reaction, chemical equilibrium. Yes. Le Chatelier. We'll talk about this. Volume, temperature. What is a catalyst? How does that affect equilibrium? Equilibrium constants, K. All these kinds of things here. Even a buffer. And we will get back into acids and bases. Okay, so this one's heavy. Let's go. Reversible reactions. And I've been alluding to this there for the past couple weeks, that a reaction, there's basically only one reaction that kind of just goes forward, and that's with a strong acid or a strong base. It only goes 100% one way, doesn't go back. But when you're talking basically every other reaction, there is a reversible thing happening here. And here is this nitrous oxide, nitrogen dioxide, at 25 degrees. If we heat it to 90 degrees, something happens, it changes. And what I want you guys to take from this is, here I didn't add anything. I didn't, I don't have my witch's brew here and I'm adding this and eye of newt. No, this is a closed system. Okay? And this is what goes on here. I don't need to add anything to it. All I needed to do was heat it, and this switched over. to a completely different beast. Okay? Here we've got brown gas. We've got 2 moles of nitrogen dioxide. And then I can produce dinitrogen tetraoxide. And this is an enclosed system. And this is one of the things that I want you guys to focus on there today is this whole idea of this in a system. It's closed off from the rest of the world, so we can kind of manipulate this. And today we're gonna see what happens there when we fool around with temperature, and pressure, and all these things. And by the end of it there today, you guys will be able to predict what's going on. Sorry, here we are. Chemical kinetics. Okay, the study of reaction rates and reaction mechanisms. Factors that can affect the rate of reaction. Like if we increase the temperature, what does increasing the temperature do to the molecules? Starts to speed them up. So if all these molecules are speeding up now, what is the likelihood of a reaction happening? Well, it's better because now these molecules are moving and the likelihood of creating a collision, because that ultimately is how a chemical reaction happens. You have atoms or molecules that have to come together in space and time and connect, and then choom. That's how it works. So you need those collisions to happen. Temperature and a catalyst will do both. I have all these multiple choice questions, and I've given you the answers because I don't have time to fool around, and I'm sure you guys can appreciate that. Equilibrium is reached in a chemical reaction when the reactants are completely consumed, so the reactants are gone, and all we have left is products. 2, the concentration of all reactants and products become equal, so here we have 50-50. All a reaction means when it is in equilibrium is that the forward rate is equal to the backward rate. So I am producing things at the same rate, forward and back, so therefore there's your equilibrium. Now, depending upon the reaction itself, which I'll show you, maybe your equilibrium is like this, but it's still happy. And it will stay like this until you do something to it. We'll show you. Le Chat. Okay. Let's get back to that closed system again. It is separated from the outside world. If a stress is applied to this system, the system will react to counter that stress. And I'm going to make a silly analogy here, but if you start shouting at this system, it will put earmuffs on and turn around. All right? Just the whole kind of a thing. And this is what we're going to do with. What kind of things can cause stress? Change in concentration, change in volume, change in temp. And let's have a look here. So consider this reaction here. I got hydrogen plus nitrogen produces ammonia. Molar ratio is 3:1:2. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. We add hydrogen to the system. What happens? So think about this. It's in a closed system. I've got hydrogen in here. I've got nitrogen in here. Initially, I had hydrogen and nitrogen, right? And I had 0 ammonia. But then, they get moving and shaking and doing their thing, and then all of a sudden there's some ammonia in there. So I have hydrogen, nitrogen, and ammonia in here. And the forward reaction is moving the same, so I'm creating everything at an equal rate. Everything's happy. But what happens now if I dump a whole whack load of hydrogen into this system? It will always do the opposite. So here the system is at equilibrium I just dump a whack load of hydrogen into the system, what's going to happen? It's going to have to compensate, so it shifts to the right. Because remember, at equilibrium, the forward reaction is equal to the backward reaction. But now I've just dumped a whack load of reactant into it, so this thing is going to move to reactants. I'm going to start making more of this stuff. And then eventually I'll get a new equilibrium. Originally my equilibrium was here, but I just dumped a whole load of hydrogen in, so it's going to force it to the right, to the products, and eventually I'll get a new equilibrium. And just, this is a chart. I don't think it'll mean much to you right now, but once I have a whole bunch of these questions here, 4 or 5 of these questions, and then you'll be banging these out. These are not bad. These are freebies on a test. Okay? Trust me, you'll see what I mean. Stressor, I can add reactant. Where's it going to shift to? The products, right? If I remove reactant, so I'm taking away the right-hand side of this. I'm removing the reactants. This thing is going to shift and make more reactants. If I add products to this system, it's going to shift the other way. Everything, if I dump it here, this thing is going to kick up on the other side. If I remove products, this thing is going to shift to the right. Don't worry about this. It's better just to show you. I just wanted to have a look here. So here I've got copper, and ammonia is producing this guy here. This has a nice pale blue color. This has a royal blue color. Again, it's in a closed system. What will happen when aqueous ammonia is added? So what if I add more of this? It's going to shift right. Because you see, I have too much of this for an equilibrium because I just added it. And so this thing is going to shift. I've stressed the system, and now it will move to a new equilibrium. So it's going to produce, it's going to shift right. Have a look at this one. I'm not going to say anything. I'm going to let you guys look at it for a second. I'll read it. So here I have acetic acid, vinegar, and agua. And so, so a hydrogen is going to go over here and make H3O plus. So that's probably a conjugate acid right there, which means that water here is a base. That's from last week. Anyway, so, and I've got my acetate ion over here. What will happen if you add base to this? Now you have to think, I'm adding a strong base here. Where is this going to attack? Is it going to attack here? I guess it could. It's kind of a weak. Is it going to attack here? I guess it could. Bases are going to go straight for acids, strong acids. So, and this is what we got here. This is the strongest acid. So what's going to happen here? This guy is going to mix with this guy and make water. So that means that my hydrogen concentration for the whole system is gone down. So hopefully there you can see that this thing is going to shift right. Because this is going to suck this out of the system. Sorry, I just did that. All right. And in order for this system to be in equilibrium, it's got to have that. So therefore now it'll shift right. I got a whole bunch more of these. And feel free to ask questions. Please ask questions. Have a look at this one. Same equation. Vinegar, water produces hydronium and acetate ion. Okay? What will happen if you add sodium acetate to the following equilibrium? So this is a salt, sodium acetate. It'll break into sodium ions and acetate ions. What am I adding to the system? I'm adding acetate ions to the system. Where is that going to go? That's going to go here. So all of a sudden now I'm flooded with acetate ions. Which way is the system going to shift? It will shift left, because I've got too much acetate, because I'm adding it here, and you'll force it there to shift left. Any questions? I've got about a whack load of these, so hopefully these aren't too bad. You just got to predict if it's going to go left or right. In which direction will the point of equilibrium shift when the concentration of nitrogen increases in the following equilibrium? Well, if I increase the amount of this whole system has to shift right to get rid of all this extra nitrogen, because there's too much there for an equilibrium. So the whole system starts making ammonia, which then decreases the amount of nitrogen. That's all these guys are. What are we doing here? In which so when the concentration of the sodium ions increases, so I increase the amount of chloride, this thing is going to shift left. Same example there before. Okay, what color will the following equilibrium be if hydrochloric acid is added here? So here we've got an acid. I don't know if I'd ask you this one because there's no acids or bases in here. And this one here, don't worry about. That is slide 15. Yeah, I wouldn't ask anything like this because there's no acids or bases in here. But, yeah, maybe. What do you guys think? Is there a base in there? Can you see a base? It's not so obvious. And this is one of the things I want you guys to know. Know at least one weak acid and one weak base. Okay? There's a list of all the strong acids there from last week. There should be a list of strong bases, anything with an OH basically. But a weak base, ammonia, is a weak base. So this indirectly is going to produce hydroxide. But if I add hydrogen here, that hydrogen from here is going to attack here. Okay? And this one here, I don't really like it. I'm going to delete that one. Let's move on. I can do that. So, slide 15. Delete it. Let's have a look at this one. In the following equilibrium, as I2 is added, what's going to happen? The concentration of H2. So now I've moved on. I'm dumping iodine into this system. It's going to shift to the right. But that's not what the question is asking. What's going to happen to the amount of hydrogen? So if I dump iodine into this system, it's going to shift right. And if it shifts right, what's going to happen to my concentration of hydrogen? It's going to go down. Okay? And if I'm going too fast, I don't hear any questions. My microphone's not turned off. All right. That happened there one time, yeah. But if you guys are having any questions, just shout out. The video will be posted as well, so you guys can stop and start it. What we were talking about there with these ones were, concentration. Increasing the concentration, decreasing the concentration, these kinds of things. But there's also the effect of volume. And if you look at these two balloons here, a decrease in volume will increase the pressure. And we'll get into that there next week. There it's Boyle's Law. But let's say I have 5 liters of gas in this balloon. There we go. 5 liters of gas. And it's in this balloon. And that's my 5-liter balloon. But if I take pressure and I start pushing it in, so I increase the pressure, I decrease the volume. Okay? And just think about it. Let's say you're in a room and there's 10 people in this room. Okay, everyone's, we're touching shoulder to shoulder, but the TV's on and we're all right. And there's hors d'oeuvres on the table. Everyone's all right. It's a little cramped, but it's okay. But then all of a sudden now you take these 10 people out of the living room and you shove them in the bathroom. Nobody's happy. Everyone is hot under the collar. Everyone's under pressure. The pressure's increased. It's hot and it's sweaty. These kinds of things. So this is what we're talking about there when you have to think about the atoms under pressure here. They're just like people. They don't want to be under pressure like this, but they are. And it's still in there. All the atoms that were in there at 5 liters are still in there. And they're not happy. And they don't really want to be like that. They want to have some elbow room. Just think about that when we do these next ones here. So the reaction will shift to the side with the smaller number of molecules. Watch and see. So, how will a decrease in the container volume affect the equilibrium concentration of ammonia in the reaction? So here, how many moles do I have on the left side? Well, I got 3 moles and 1 mole. So I have 4 moles of gas on this side, and I have 2 moles of gas on this side. And I know that you look at nitrogen here, it's a nitrogen atom and a nitrogen atom together. All right, and the hydrogen is a hydrogen and a hydrogen. And okay, there's your molecule, H2. There's your molecule, N2. Look at this molecule. 1 molecule of this is 1 N with 3 H's coming off of it. This molecule is definitely bigger than this one or this one. Negate this. We don't worry about this. In chemistry at the atomic level, one of this molecule has the same, occupies the same space as this guy. So we're not worried about grammage or molar mass or anything like this. The only thing we're worried about in this style of question is the number of moles. So I got 4 moles on this side. I got 2 moles on this side. What will happen if I decrease the container? Are we going to stay at 4 moles or are we going to shift to 2 moles? The whole thing will shift to the right because now you've limited the amount of space available to these molecules. So the molecules will just shift over to the right and start making 2 moles of ammonia. What would happen if you decrease the pressure, increase the volume? It would shift back to the side with 4 moles because there's elbow room. We got room to move. We can shift. Let's try this one here. How will a decrease in container volume affect the equilibrium concentration of hydrogen? So I have 2 moles on this side. Don't count these guys. Count the number in front. So I have 1 and 1 is 2 moles. And over here, I also have 2 moles. So if it shifts one side, it's still 2. If it shifts the other side, it's still 2. So if I decrease the volume, increase the pressure, this thing won't shift anyway because it doesn't matter. Because if it shifts to one side, it's still 2. Stays at the first side, it's 2. Doesn't matter. So here, decreasing the volume has no effect. Okay. In which direction will equilibrium shift when the volume decreases? So again, I decrease the volume. I have 1 mole here. I have 2 moles here. This is going to shift to the left. How are we doing? I'm going to take I don't know, I'm not going to take a timeout, but I just want to take a break and just hear any feedback anybody has. How is this doing? Is it any issues with this so far?
I have a question.
Yeah, shoot away. Thanks, Samantha. Thanks, Aisha. Go ahead. Who am I speaking to?
You're speaking to Hunter.
Mm-hmm. How's it going?
Good. So,
Where am
why does the equilibrium always shift to the side with the smaller amount of molecules?
In this case here, because we're moving everybody from the living room to the bathroom. You know what I mean? We're making the volume smaller, so the molecules are uncomfortable because now they're always, there's too many of them, and what they're going to do to compensate the lack of space, they're going to decrease their own numbers. Yeah, kinda. Talk to me, Hunter.
So then would it just completely get rid of those molecules by shifting, like a liquid to a more concentrated container? Would it just like completely lose them? So then if I poured it back into the larger container, I would still have lost those molecules?
Ah, good question. For all these guys here, excellent question. Awesome, spot on. Remember, it's a closed container. I can't get in, they can't get out. All right? So, and here, this system is at equilibrium. And at this particular equilibrium, at this particular temperature, right? So, for this question here, my reactants, I have 1 mole. Products, I have 2 moles. So in my vessel right now at equilibrium, I got 3 beasts in here. All right? But then if I decrease it, I'm making all 3 beasts unhappy because they're under pressure and they don't want to be. I've created a stress. So what will happen is I decrease the volume, this thing will shift and start making PCl5. All right, phosphorus pentachloride. All right, until a new equilibrium is met at this conditions. And to answer your question there, the second part, if we released these conditions and went back to our original, it would shift back and start making more products until we had our original equilibrium. Talk to me, Hunter. Talk to me.
Okay, so then just in that case, the phosphorus pentachloride, like it would make those, but they wouldn't react with the stuff on the right.
They would, because let's say this is our equilibrium right here for this question that I'm looking at the board right now, and for the vessel size this big. But if we decrease and it's going to shift towards the reactants, now wherever we have a new equilibrium where the forward reaction equals the backward reaction. But maybe it looks like this. Who knows what it looks like? Whatever is going, that's what's going on in the little reaction vessel. And there's still an equilibrium going on, forward and back. But it's just happening at a different rate now because we've changed the conditions. But if we want to revert back to our original, which is what I'm looking at right now, get the container back to its original size, and then this thing will shift. I've got a lot.
Okay. I would say I understand that 88.5% of that.
Take it and run. See you tomorrow. But I got a lot more of these. We'll get that other, what is it, 11.5%? Let's go get it. Let's have a look here. In which direction will equilibrium shift? Jeez, man. When the volume of the reaction vessel increases. So now, this is our equilibrium now, and you'll see there our equilibrium. Now I'm going to increase the volume. So what's going on to my leg room now in economy class? Everyone's in first class, right? There's lots of room for everybody. So now we're going to shift so everybody can join the party. And because there's more room, I now am able to stuff 3 moles. So this thing is going to shift towards the right. All right? And remember, it's going to find a new equilibrium. Forward reaction is going to equal the, but it's a different scenario than the original one there that we were looking at here. Let's try another one. I got a whack load of these. In which direction will equilibrium shift when the volume of the reaction vessel increases? So here, we're increasing. How many moles do I have on this side? I got 1 mole. But wait a second. I got 2 moles on this side, but I'm increasing it. And please write this down. You see his chemical equation there? You see a silver chloride produces silver ions and chloride ions and all this. You got to be careful now because you guys learned these back in 1008, but haven't really gone on to them. Now I'm going to get you on them. Not only are you going to have to read or produce a chemical reaction, which you guys can do, you've got to take notice of these guys here. Aqueous, solid, liquid, gas. Now they fall into play because you will see that solids, no go. There's no chemistry that involves just a solid. Because a solid there's no medium in which to make atoms have collisions, right? Solid is just a block. Nothing's moving from that. So in this case here, on the left side, we've got a solid silver chloride, and we've got this guy here. It's not going to affect anything. Pressure and volume only affects gases. Okay, so for this one here, there'd be no shift because of this guy. Okay. The last part of Le Chat's stuff is dealing with temperature. If you increase the temperature, you're increasing the rate of both the forward and the reverse reaction, right? Because of kinetic molecular theory, KMT should sound familiar. You increase the temperature, the molecules are moving, greater chances of having a collision. But the application of heat to increase the temperature favors the reaction where heat is a reactant or heat is absorbed. So let's have a look here. Have a look at these 2 reactions. Here I have A plus heat produces B. Okay? Endothermic, where the heat is absorbed. Okay? And I think you guys did that there last no, you wouldn't have. Yeah, there's a really cool lab there. The use yeast and peroxide, and you can make your solution heat up and make it go cold. And but in this case here, if you add heat to the system, okay, it's going to shift right to the side where there is no heat. Here's an exothermic reaction. These are the things that go boom. Okay, here you have whatever you're igniting, boom, and it changes into this and heat. So adding, look at this one, adding heat to this system. So here I've got this system, it's in a closed container. A is producing B plus boom. What if I add more boom to this? It's going to shift the other way, away from the boom. Whatever you add to it, it's going to shift the other way because you'll have too much of that in the system. Let's try some. So you got, and again, this one here. It depends on the heat. It moves from here to here. Let's look at this one here. These are exactly the type of questions you'll see on your quiz, your assignment, your test. Okay, so except there'll be multiple choice here. How will an increase in temperature affect the equilibrium concentration of ammonia in the reaction. So here I've got hydrogen plus nitrogen is producing ammonia, and boom. So if I add more temperature, which way is this going to go? Well, we've already got temperature on this side, and if I add more, it's going to shoot this way. It's going to shoot left to the side where there is no temperature, no boom. Okay? Any questions on that? Give a shout out. It's okay. It's new stuff. So if you guys have questions, please ask. Please.
I have a question.
All right. What do you got?
So then, with a chemical where
Hunter,
you know,
sorry, what slide should I look at? This one or?
doesn't matter. It's just about temperature.
Oh, okay, yeah. Go on.
So if the temperature, it produces heat. So then, would it always produce heat, or is there a finite amount that it can produce when two chemicals react, and then eventually the product is heat? Is there a finite that equation can happen, or will there always be at an equilibrium so that the heat is always produced?
In this particular case, the heat is being produced, and so the reaction vessel is getting hotter. And so if you heat this reaction vessel that's actually getting hotter, what's going to happen? It's going to stop getting hotter. And that tells us that it's now shifting to the left where there is no heat because you're adding heat to it artificially. How does that make sense?
I'll ask at the end of class. I think it's more complicated than...
That's all good. It's all good. And I think someone just asked, was it Catherine there asked a question? Le Chatelier's principles do work together. For what I'm doing here, know these three types of questions. Because these are the questions there. I wouldn't combine temperature. I don't think so. Unless... maybe a bonus mark or something, but just to be able to, all I'm looking for is for you guys to recognize that if you add heat to a system, it'll shift one way. If I add more moles of reactant or product to the system, it will shift one way. Okay? If I decrease or increase the vessel size, it will shift one way. That's all I'm looking for. I'm not looking for anything massive. Right here, bang. This is an exam question. Guaranteed. I'm just going to change the numbers. Okay? Did I just say that? Oh, no. Horrible. Hopefully that answered your question there, Catherine. I think it was Catherine, and if I didn't, just you can shout at me there later. Okay, thanks. What do we got here? In which direction will equilibrium shift when the reaction vessel is cooled? Well, if it's cooling, okay, it'll shift to the left. All right? Because where's the heat? If you're cooling the whole system down, the system is going to be looking for the heat. Which side's the heat? I see the kg on the left. Shift to the left. Next question. Hey, man, we're moving faster than I thought. Well, I guess it's been an hour. It's all right. Catalyst. Oh, yeah, you'll see something on here. And if you haven't seen it already, there in bio, you guys will be all over this, man, when you guys get into proteins and enzymes and hormones, these kinds of things. A catalyst is a substance. All it does is it influences a reaction. And... like amylase in your mouth, if you chew a piece of bread there for 5 minutes, it goes sweet. Because amylase in your mouth, these little enzymes that go into starch molecules and break it. And the amazing thing about these catalysts, they come out and they're able to do this again. And that's the whole thing with the catalyst, is that it affects the reaction in a certain way, speeds it up. It doesn't really speed it up, but you'll see there by the next slide. But it comes out of the reaction. It's not a part of the reaction, but it absolutely influences it. And you have to think your body there, billions of years in evolutionary process there, the whole idea of using enzymes to get things done, gee whiz, I tell you, it's amazing. It's amazing what these enzymes can do. We'll get into there the energy of activation energy, and I'm not going to explain, I'm just going to show it to you. This is a chemical reaction. And you see why chemical reactions aren't spontaneous, don't just happen on their own. Like dynamite. You just have a stick of dynamite here on my table. First, I would say get it off my table, but I would secondly realize that if there's no fire around, then that dynamite is harmless. Okay? And it is, until it's surrounded or provided with an ignition source. So that dynamite is here, and it's sitting on my table. We're actually playing frisbee with it, or the dog, I'm throwing it, and the dog is catching it and bringing it back, right? But in order for that dynamite to become lethal, I got to ignite it. So I'm adding energy into the system. And I keep lighting it. And then at some point in time there, boom, it ignites. And that's where you get the boom. And now this energy is released. And now it's going on its own. And it's like a ball rolling down a hill. It will stop on its own. And that's what is happening here. And you'll notice there that the ball, when it eventually stopped at the bottom of the hill, of course, it's lower than where it was. Lower potential energy. And from here to here, we've now recouped that energy in some fashion. Or we were able to use this energy for some biological source or whatever. But the whole point is, at rest, we have to put this amount of energy into it in order to get the reaction to go. It's pretty costly. And you think about there from a biological point of view, in order to get anything done biochemically, I got to keep inputting all this energy. How many bananas can a person eat in a day? Aha. Let's get some enzymes. Let's get a catalyst. And what this does is these enzymes, they reduce this energy of activation that's required in order for this reaction to go. These enzymes, all they do, you don't need as much anymore. So instead of putting all of this extra energy in, and that's a lot of work. And you think that there's a billion chemical reactions going on in your body at this very moment. If we only have to use half the amount of energy to get the same reaction, the net gain out of it, then that's what that's the whole point. Have a look at this one here. In which direction will the point of equilibrium shift when a catalyst is added to the following equilibrium system? Well, catalysts are not a part of the chemical reaction. Catalysts don't affect it in any way other than lowering its energy of activation. So this catalyst will not affect this reaction at all in any way. Okay? Doesn't affect its equilibrium whatsoever. Great question. Like it. You'll see that one again for sure. Okay. All of these there were Le Chatelier's principle. It's all about equilibrium, finding and changing the conditions of the original equilibrium, and you telling me where the final equilibrium is. All right, and have a look at those. Try those again, and they're good. They're good. You'll see them there on today's quiz there this afternoon for sure. I think. Maybe on the assignment too. Okay, but anyway, we're on the second half. If you're just watching this video from YouTube, you might want to take a little break here. Anyone watching this live, kick around. This is good stuff. K is just our chemical symbol there for equilibrium constant. All right. Last week there we did Kw. The K, the equilibrium constant of water, which was hydrogen, the concentration of hydrogen times the concentration of hydroxide. Multiply those two bananas together and you always get 1.0 times 10 to the negative 14. All right. Here we're talking about chemical equilibrium. And for every equilibrium, and you'll see there I've got small a, big A, small b, big B, small c, just long as you guys know that these are the substances there. I don't know, sodium hydroxide, calcium sulfate, these are my compounds. And these here, they represent the molar ratio. So that could be a 3, a 2, could be a 1, these kinds of things. And I'm just going to show you this without really explaining it to you. Please remember that when you have a reaction like this, and I'm going to ask you to make me a chemical equilibrium equation. Products over reactants. Products over reactants. So here are my products. Here are my reactants. Okay? So I'd go K is equal to, and remember square brackets is molarity, moles per liter. And whatever number you had out front here, that's now an exponent. Okay, and that will come into play. If you have a 1 here, let's just say it's just the letter C here, and there's a 1 here, but we don't write 1, all right? Then that would be, sorry, I can't, that's an image, but there wouldn't be a C exponent there. There would be a 1, but you wouldn't have to write it. So let me, I'll show you this. Only substances whose molar concentrations can go into what we call the mass law expression. So you guys already know that we're not using solids in these expressions because solids have no way of allowing atoms or molecules to collide. Well, we don't use liquids either. And what I mean by liquids, pure liquids. If you see water, H2O, with a little subscript L, which I'll show you, we don't use those. You remember last week there when you're doing your spectator ions and the net ionic equation, we didn't use these kinds of things. So we're only going to use gases and aqueous solutions, AQ. I'm throwing these words out at you. You'll see what I mean. You will. Have a look here. For the equilibrium, so here I have 3 moles of hydrogen, 1 mole of nitrogen, and 2 moles of ammonia. And please notice, please take note, gas, gas, gas. So this one here is good to go. If I asked you there to make an equilibrium expression, products over reactants. So here's my ammonia, slap it in between 2 square brackets, and there's 2 out front, 2 goes behind as an exponent. I got my guys here, they go down here. Okay, and it's just as is written. Remember H2, 1 molecule of H2, okay, that's its own thing. So don't worry about the 2's down here and all this. Whatever's there goes inside the square bracket. If there's a number out front, it goes as an exponent. So the value of KEQ, I haven't even told you what KEQ is yet. We'll get there. KEQ is determined by this expression. And it's the concentration of ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. What does all this mean? First thing, you've got to be able to make this. What does all this mean, though? we can figure out what is happening. What you did over here, all these questions here with Le Chatelier's principle and all this, okay, you're predicting it here, you're predicting it here, and, you know, you can do that visually, but you can also do it mathematically with K, E, Q. And you have a look here. Where are we here? We're right here. And you're looking at this going, okay, well, I've got these reactants here, and I got the products here, and where is this expression at equilibrium? Is it basically 100% products, or is it 100% reactants? Or is it about 50-50? Those are basically the three things there that we need to know. Looking at this reaction, where is it? Because I'm looking at it now, and K is just a number. And the value of K will tell you where this reaction is. If K is a large number, greater than 1, so like 2.5, 18, 250. If K is a large number, it will favor the products. Okay? If K is a really small number, less than 1. And some examples are 1.4 times 10 to the negative 3, small number. 4.7 times 10 to the negative 9, small number. If K is a small number, your reactants are favored. So if K is a big number, that means that just generally looking at this expression, most of the container is going to be that, if K is a big number. If K is a really small number, most of it will be on the reactant side. If K is around 1, so 1.5, 0.8, somewhere in there, now we're looking at about 50-50. So 1 is the magic number. If K, whatever, and I'll show you how to figure out K, it's just plug and play. But if K is big number, that reaction is going to be mostly products. If K is a really small number, it's going to be mostly reactants. Because we're just trying to figure out where this reaction is. Is it going this way or this way? And if K is around 1, there you go. Then you're about your 50-50. It's about 50% products, 50% reactants. Okay? You will have to know that one. Okay? So have a look at this one here. Now, did I have any... Yeah, get out of the way, will you? Animation. Is it here? Yes, it is. Slideshow. Good. Hey, where did my animation go? Why didn't that go? It's not letting me. Okay, it's not letting me on sharing. Oh, well, that is horrible. How am I supposed to do this? Okay, good enough. Okay, so my animation is pooched here. It's all right. Calculate the value. So here I'm going to show you, again, this is an exam question. Promise you. This is a quiz 2 question or an assignment question. This is exactly what you're going to see, and your question there will be multiple choice, maybe on assignment, I don't know, do we have another assignment? No, assignment 2 doesn't come out until after reading week, so definitely you'll see this there on quiz 3, okay? And the test there, week 7. Calculate the KEQ for the following equilibrium. Okay, KEQ, that's going to be your products over reactants. So, formula is coming. And here, I give you the actual molar concentrations of each of these guys. So here's your reaction. H2I2 produces 2HI. Everything's balanced. Gas, gas, gas. Everything's good. So I make my KEQ. my equilibrium constant expression, plug it in. So HI, I've got 2 of those, so I got to square it. Here I got H2 and I2. I just throw those down because that's 1 mole and 1 mole. Bang. No exponents. Well, there's a 1 there, but yeah. We good? Now, question is asking to calculate KEQ. So I need to figure this out, and I've given you the concentration of H2, I2, and HI. So plug them in. I've given you the molar concentration, so there you go. And you solve. Now, before I get into what that number means, start thinking about what it means, 45.9. But I'm worried about when you guys get to this point, do not plug this whole beast into your calculator. You know, you'll have a bracket 1.54, 4 brackets squared, more brackets divided by, don't do that. Please just do the top first. 1.544 times 1.544 equals what? Have a piece of paper, write it down. That's your numerator. 0.228 times 0.228, figure out the bottom. So you have one number on top, one number on bottom, and then, okay? Because these questions, once you get them, they're cake, all right? But I don't want to see you guys make mistakes on a question there that you should bang out, okay? And just be careful of the calculators. Use them for what they're worth. Throw them away when you need to, okay? Getting back to this, we've just calculated there. So looking at this equilibrium expression, okay, there's hydrogen, iodine, produces hydrogen and iodide. But at equilibrium, what is the snapshot of what's going on here? Well, we calculated K for this. And K is 45.9. Woof, that's a big one. Where would that fall into? That would fall into these guys here. Okay. And that means that this reaction here will be around the product. So mostly in the vessel, this will be products. Okay? That's how this equilibrium works. And you can see here I'm asking you to calculate the K value, and I give you the molarities. Well, I could ask you for the molarities if I give you the K value. And it's interesting to note, how many moles of hydrogen are in this reaction? 1. How many moles of iodine are in this reaction? 1. Well, look at the values there that I gave you. They're kind of the same. I'll come back to that, I promise. I just put that in there to confuse you. Yes, you're welcome. All right, now, going back to strong acids and strong bases, because we harped on that there last week, and I'm going to do a bit of harping again. Strong bases, strong acids. There is no equilibrium. And we talked about that there last week. I kind of mentioned it there earlier. Strong bases, strong acids are characteristic. Why? Because they have 100% ionization, 100% dissociation, 100% breakage. There is no 50-50. There's no equilibrium here. That's why you'll see here, I just made this generic acid reaction here. HA, just an acid, because it has hydrogen. So HA plus water, there's no back reaction here at all. It's 100% H3O and A-. That's a definition of a strong acid. That's a definition of a strong base. There's no equilibrium. Okay? 100% breakup. And you'll see here, strong acid, how many beasts do I have in here? Well, I have my H plus, H3O plus actually, hydronium plus, and the minus, the chloride ions. That's it. I only have 2 beasts in here because it's 100% breakage. But a weak acid and a weak base, it's not 100%. There has to be some equilibrium. Now, maybe it's not 50-50. I write it as 50-50, but it's not. It tends to be a heck of a lot smaller. But when I say 50% breakup, I mean some number considerably less than 100 to compare it against a strong acid or base, right? So here you have weak acids and weak bases. You've got the reversible reaction because it's not 100%. And you'll see here, this is vinegar in water. So here's your vinegar and your water. Some of the hydrogens from the vinegar are going to go on the water. They are, I promise. But a lot of the hydrogens are not going to go onto that water. So you see here in this vinegar solution, vinegar and water, you don't have two beasts like here. You actually have three beasts. You do have the hydronium ions. Some of the hydrogens did come off. And the acetate ions, these guys here, yeah, sure, they broke off, yeah. But then you have a look at the purple ones here. These are all the HAs, the vinegar that didn't break. And look at them all. They're all over the place. So in a weak acid or a weak base, you have three beasts. Okay? Now, our job is to find out where that equilibrium of those three beasts exist. It's not bad, actually, once you try some of these. Okay? I really want to try that animation. So I'm going to, hopefully, spend a lot of time at that. So we're going to try that out somehow. Have a look at this one. Because weak acid bases do not break up 100%, we can use K to find out how much acid or base has ionized or dissociated, right? Acids ionize, bases dissociate. We don't use KEQ, we use Ka or Kb. K of acid, K of base, okay? And for all intents and purposes, finding the equilibrium constant of a weak acid is exactly the same as finding the equilibrium constant of a weak base, the procedure. But for the remainder of this slide, I'm only going to focus on Ka. Okay? Kb is exactly the same. As far as I know, I don't think that there's any questions out there on Kb, but it'll just be on Ka on how to do it. And it's kind of the same as what we've already done already. So have a look here. Here I have this chemical equation. I got an acid and water produces hydronium and the acetate ion. Okay. Can you make me the Ka expression? All right. Products over reactants. What do you see here? Here I have four beasts, right? I got vinegar, agua, hydronium, and acetate. So I got four beasts here. Okay, Ka is equal to products. So hydronium, there it is. No number in front, so no exponent. Here I got acetate. No number in front of that, so no exponent there. Everything looks good. I got my vinegar. That's under there. Okay, no number. All right, no exponent. Now, wait a sec. Where's my water? Why isn't water in there? Because it's liquid. It's not involved. And it doesn't go into this reaction at all. So in this case here, products over reactants, this is one of the things I want you to be careful of. Okay, when you're making your Ka expression. Liquids, no go. Solids, no go. All right? And so this is your Ka expression. And every compound at every temperature has a different K value. So this one here, 1.8 times 10 to the negative 5. K has no units associated with it. All K will tell you, is this. That's all K will tell you. A big K, it's going to products. Small K, it's going to reactants. K of 1 or about, that's 50-50. That's it. That's it. 3 scenarios I'll be looking for. Okay? So, where am I going? So that's what this is. That there is to make your Ka expression, which is exactly the same thing, products over reactants. This is just a bit of extra. Why no Ka or Kb for strong acids or bases? Because strong acids and bases don't have an equilibrium. They're just one shot. Straight ahead. There's no back reaction. 100% breakage. Okay? Have a look at this one. And again, these are exam questions. All right. What do we got here? Which acid ionization constant indicates the strongest acid? So, strongest acid, I've been harping on strong and weak acids, and I'm still going to harp on them because there's a lot of, intuition that you're going to have in your educational repertoire to kind of answer this question. Which acid ionization constant, okay, I've got 4 of them here, indicates the strongest acid? Well, what happens in a strong acid? I've got reactants to products. A strong acid is going to break 100%. It's a one-way reaction. Strong acids, strong bases go right to products. There's no back reaction. So it's going right to products. So what are we looking for? If a K is going right to products, that means we're looking for a number, the largest number possible. Try that again. Which acid concentration here indicates a strong acid? Well, what is a strong acid? There's no equilibrium. It goes straight to products. K that goes to products has to be bigger than 1. Or in this case here, the biggest one. So which one here is the biggest one? I've got 3.5 times 10 to the negative 4. I got 10 to the negative 8, 10 to the negative 9, 10 to the negative 13. This is smallest, okay? Second smallest. And this one here is your largest. So this one here will act the most like a strong acid. What's going on for this one right here? If some acid has a Ka of 1.3 times 10 to the negative 13. 10 to the negative 13. Where is that guy hanging out? Over in the reactants. Okay? So the K, there's no centimeter associated with it. There's no meters or anything like that. It's just a number. If it's big, if it's small, or if it's around 1. Okay? That's all we're trying to find out. Decipher the reaction.
Can I ask a question?
You most certainly can. Who am I speaking to?
For Alaya.
Hi.
Hi. For slide 36, when we're trying to find the key A, are you going to give us the concentration for each?
Is it for this slide here?
Compound?
Or which slide?
Yes, because this is slide.
Okay, all right. So in this case here, there's 2 ways that I can go. I can give you the Ka, and you got to find out the concentrations. We're getting there. Or I could give you the concentrations and ask you to find the Ka. All right. So this question right here, where was it? This one right here. Yeah. So here I asked you to find me the KEQ for this reaction, and I gave you the concentrations. Bang, 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 plug and play. You get a number, choose C, away you go. Okay? That's one way. Another way is I could give you the KEQ, which I'm going to do right now, and ask you to find me the concentrations of these guys. Okay? Have a look. Good question, by the way. Thank you for asking. Awesome, Alaya. Thank you. Have a look at this one. Now, this one here, I really wanted animation, and yeah, okay, now. Aha! There we go. Okay, so now I can do this step by step, which is what I wanted. I miss the whiteboard, I really do. And I've been trying to get the whiteboard going downstairs, but I put it, my kids are 7 and 4, so the whiteboard is down by my ankles. And so I don't know, it just didn't work. So we're going to try this out. There we go, I'll get rid of that. And this is questions found on page 377, by the way. Okay. Determine the hydrogen concentration. Interesting. In a 0.2 molar solution of vinegar. And all I do is I've given you the Ka. So I'm asking you to find, I didn't even give you, see, this is where you guys are going to be. Now, not every question is going to be like this. This question here, I would give it severity. I'd give it a 7. It's a 7 out of 10 as far as a good question where you got to know your stuff. Okay? But once you try a couple of these, the pattern is definitely repeatable. So I didn't even give you a chemical equation. I just gave you vinegar. Determine the H plus in a 0.2 molar solution of vinegar, and I gave you the Ka. Well, you can't make a Ka expression until you know your products and your reactants. So if you're watching this video through YouTube and not live, but even if you want to try and make that equation. Okay? And so you have your acid, always plus water, liquid, aqueous. And that hydrogen's going to pop onto here and make you your hydronium. And what's left over from that? Like you look at this molecule here, this hydrogen right here jumped onto there. So what's left? C2H3O2 minus. It's there. And why this is important is I want to show you this. Because I give you 0.2 moles of this. So put it there. Because that's how much of this you start with. How much of this, I don't know. But what I do know is that, let's go back to what I was saying there. Here I have a vinegar molecule, and I have one. I have one vinegar molecule in my hand. Yeah, I do. And this hydrogen here jumped onto here, which made this guy. What's left over came over here. So basically, if I have one of these guys here on my screen, I have 1 and 1. Would you agree? If I have 5 of these guys over here, how many of these am I going to produce? 5 and 5, right? Because everything's got to go somewhere. So I don't know how much this thing breaks because it's vinegar. It's a weak acid. I don't know. It doesn't go 100%. It goes some percentage. That's what the question is trying to ask me. So I don't know how much hydronium I've made, but whatever I do know that this amount will 100% equal that amount. Okay? Hydrogen jumps off here, goes to here. There's one of them. This acetate ion is left. So these two guys will be equal. Okay, this is crazy important, this step right here. Okay, being able to break it down initially, I had 0.2 moles of this, but some of these guys are going to ionize. How much? I don't know. But whatever they do ionize, I will have equal amounts of. Because the hydrogen that's on here was on here. Okay? So once we've got this information here, now I can make my Ka expression, which is just products over reactants. Okay? So I got my hydronium and my acetate. Here, easy peasy. All over my vinegar, which is down here. And remember, no water, because it's a liquid. All right? So here's my Ka expression. Now plug and play. That's it. What information did I give you? Okay. That's what I've given you so far, even though I didn't really tell it to you. But now you know. Secret's out. Okay? So you don't know what these guys are, so put them at Y. Or put an X. Put a happy face. So you'd have happy face times happy face. Works for me. All right? I also gave you the Ka. So take your 1.8 times 10 to the negative 5, plug it in here. So here I have 1.8 times 10 to the negative 5 is equal to y squared divided by 0.2. Come on, say flip. Sorry if you can't see that. It's y squared is equal to 1.8 times 10 to the negative 5 times 0.2. So what I did was I brought this 0.2 over here. If you're having issues with algebra, email me, because you're going to get this there in the physics as well, and you've got to be able to manipulate a formula. Like a little bit of homework, a good little practice there for homework. If area, like take a simple formula, like area is equal to pi r squared. We've all seen it before, right? Area is equal to pi r squared, right? That formula is written in terms of area. Can you flip that formula around, same formula mind you, but make it in terms of radius? Area is equal to pi r squared. The A is by itself. Can you flip this algebraic formula around and get it in terms of r? If you can do that, then you're in good shape as far as formula manipulation go, which will go a long way more so in the physics, okay? But you see right here, we've got y squared is equal to all this. Sorry, I guess that's, it's y squared is equal to 3.6 times 10 to the negative 6. And then opposite of squared, because I don't want y squared, I want y. And you do the square root of both sides, and this is the answer there you get. And you'll see here that I started off with 0.20 molar of this. And at equilibrium, these guys here, their molar concentrations are 1.9 times 10 to the negative 3. Like, it's crazy small on a scale 1,000 times less. So these guys here are very small, and that's why a weak acid is a weak acid. Look at vinegar. The amount of hydrogen it has in there, not dangerous, just enough to give you that tang that's really good with your salt and your French fries. Okay? Let's try another one. Again, same style of question, just change the numbers around. So here I've got hydrocyanic acid, and pause this if you're recording it, or if you're watching it there or whatever, pause it and try it. Okay? Hydrocyanic acid, HCN, is a weak acid. I try and give you as much information as possible. And so whenever you see weak acid, woof, this is where you're at. You know that there's going to be a bit of work involved for this question. And this hydrocyanic acid has a Ka of 4.0 times 10 to the negative 10. What does that tell you about this acid? Is this thing a strong acid, or a weak acid, or even a crazy weak? Well, it's 10 to the negative 10. So that's crazy small. So that K value is telling me there that this thing wants to stay as reactants. Doesn't want to break up. But let's have a look here. Here I'm asking, what is the hydrogen concentration in a 0.10 molar solution? So hydrocyanic acid plus water produces hydronium. Okay. Now this is where we need to fill in a little bit more. And as I said, this little box here, this little rectangle underneath, This is crazy important because this sets up everything. You can't do this question if you don't do this step. Okay? And remember our reasoning. I gave you this. Okay, that's 0.1 molar. And if this does break, which it really doesn't because the Ka is 10 to the negative 10, this thing doesn't like to break at all. But if it does break, okay, I'm going to get, if one of these breaks, I'm going to get one of these and one of these. If 10 of them break, I'm going to get 10 and 10. The point being, this number here will be the same as this number here. All right? So, we do our Ka expression, which is products over reactants. No water. All right? Plug and play. What did I give you? I gave you 0.1 molar for your HCN. These guys here are X and X. I've given you the Ka. Let's rock and roll. So my Ka is 4.0 times 10 to the negative 10, which is equal to X squared divided by 0.1. Just plugging in the information there that we got. And I flipped everything around. X squared is equal to this times the 0.1. And you just follow it along. And there we go. So this is the hydrogen concentration of this solution. But it is also this concentration as well, right? Because these guys here are both the same. So I could ask you, what is the hydrogen concentration? I could ask you for the conjugate species of it. Okay? That kind of a thing. Talk to me. I'm going to take 30 seconds. I'm going to drink my coffee. Anyone have questions? Talk to me.
Will there be a lot of these questions on the test?
Hundreds. Hundreds.
Thousands.
Yes.
Millions, I gotcha.
Yeah. No. I don't want you guys spending, like, I've given you guys these quizzes there for a week and all that. Your final exam will be, I'm not going to spread it out over a week. Thank you for that. I read that comment. That's good. I'm not going to spread this exam out over a week. It'll be on a day. I'll give you guys, 8 hours or 12 hours to accomplish it, but it will be done on one day. And, an hour and a half test, if you know what you're doing, you should be in and out, in an hour and a half, an hour. I've even had people get out of my exams after 20 minutes and still rock it. Okay? But I don't want you guys sitting there for 5 hours and all this kind of stuff. So yes, there will be questions like this, but they are kind of involved, and you're going to need a lot, please make sure you guys have some scrap paper. And on a test, there might be 2 of these, more different styles, but it's not going to beat you guys. You do it once, why would I get you to do it twice? It's just overkill, right? I'm just kind of padding the pillow, and I don't want to pad the pillow. There's a lot of things in this course, and basically, if I can hit on everything for one question, which is impossible because your week 7 exam will be 50, 60, 45 questions, somewhere in there, and 2 minutes a question, but you guys will have lots of time to do it anyway. I want you guys to be done in an hour and a half. That's a fair test because I'm testing you on everything. My tests are good. Don't take them lightly. Okay? My quizzes aren't 9 questions long either. My quizzes are 20 because I give you time to do it, and it allows me more ability to test you on everything. And but I don't want you guys sitting there for 5 hours doing no. So the answer your question, long and short of it, there will be questions on there like this, but hundreds. No, I was joking. Hopefully that answered. And we're into the last one. And so we did KW last week. We did Le Chat's there today. We did KEQ. All right. We've done KA, which is KB, but we're not going to do KB. I'm just going to focus on KA. All right. and this is, as far as I know, the last one here. This is called the solubility product. And here's another K. And all this means is, I'm going to get out of this. You see, when you put your sugar in the water or whatever, salt in the water, eventually there comes to a point there where the water just ain't taking any more sugar. That's it. Full. I'm saturated. Remember that one? Unsaturated, saturated, supersaturated? Okay, so our solution is saturated. There's actually sugar crystals down at the bottom. Okay? Just like this one. But, so this water here can't take any more. But just the same way that water auto-ionizes, there's always something going on here. Because these atoms are moving and shaking. And there's always something going on. There is something going on here at the very surface of the pile of sugar there at the bottom. Some of the sugar is coming out of solution and going onto the pile. Some sugar from the pile is going back into solution. Okay? And that's what this KSP is measuring, is the ability of that solute to go in. And it's all about your K. So what does a big K mean? It's going to the right. What does a low K mean? It's staying at the left. All right? And have a look at these ones right here. And it's why I asked you guys to take notice of the subscripts now. Because here, we've got calcium fluoride produces calcium ions and 2 moles of fluoride ions. Calcium fluoride is a solid. We no use the solids or liquids in any of these. So we define the solubility product, KSP, same everything, nothing's changed, is products over reactants. But because in this situation here our reactants are a solid, we ain't got no reactants in the equation. So for these guys here, your KSP question or your KSP equilibrium equation is just products. Okay? And just be careful. 2 moles here. There's a 2 up there. Okay? We'll get into more of these. I have a whole bunch. Okay? So now this is the last K. And it's all here. This is your formula sheet. Okay? So here's your KEQ. And I've also put for KA and KB as well. All right? And so KEQ, KAB, products over reactants. And I've tried to make a little formula here. If there's 3 moles in front, then there'll be 3 moles exponent. Okay? Let me know if there's any issues with that. Remember, solids, liquids are not included in these. Okay? Here's your KSP, what we're just doing now. And you'll see there that there are no reactants because the reactants are a solid. So it's just over 1, which we just negate anyway. And here's your chemical reaction. For B is a solid, produces 2C, aqueous, and D. Well, B is a solid is a no-go. Okay? Yeah. So that is for your formulas. So it's all there. Let's try one. KSP, the equilibrium constant there for a solid dissolving in a liquid or aqueous solution. KSP indicates how much solute you can dissolve in the solution. And a highly soluble, if something is readily going in, it's going to have a high K. If something is not dissolving well, it's going to have a low Ka. Or sorry, a low KSP. The Ks work the same. High K, it's going to the right. A low K, it's going to the left. Standard reactants. Professor Dave, I was digging through videos and I like them. And I use them there for a lot of my videos for physics as well. This is a really, 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 really good little movie. And I think it's like 5 or 6 minutes long. And maybe the sound of my voice just feels like somebody grating their nails against a chalkboard to you. Well, here, watch Professor Dave's 6-minute little video there, and you'll get it. It's not bad. Everything I've just said, he says it a different way, and if you don't get it with me, watch this video and you'll be all right. Okay? I can't, but on this forum, but let's have a look here. What is going on here? I don't like that. I guess that's going to go up there, right? Okay, good enough. See if I can change this onto here. There we go, so we can see everything. Now, what do we got? Have a look at this one here, start to finish. Calculate the solubility. Okay, so right then and there, that's what KSP. All right, that's where we're in and about, right there, when you see that solubility, right? So calculate the solubility of silver iodide at 25 degrees. And the silver ions and the iodide ions if KSP is 8.5 times 10 to the negative 17. So we're going to do things exactly the same way. You're going to make your chemical equation. All right? And look at my KSP. What's already happened? What can you tell me by this number? 8.5 times 10 to the negative 17, ridiculously small. This thing is going to be hanging out. This thing is basically insoluble. That's what it's telling us. But 10 to the negative 17, what's that, 17 zeros? I don't even know how many that is. What is that, 100 billion trillion? I don't even know. But that's how many like 100 trillionth of an atom. If you have a trillion atoms, one of them is going into solution. This thing is basically insoluble. But same thing. We do our chemical equation. So we got silver iodide solid produces these two species there, aqueous. Now you notice this guy does, if he does break up, which they really don't, if one of these guys does break up, well, I got 1 and I got 1. Right? If 5 of these break up, I got 5 and I got 5. Whatever it is, these numbers here will be the same, just like the Ka. Okay? So now, because we don't include solids, our KSP equation is products over no reactants. Okay? Now, what are we going to do? I've got KSP, and I've got these X's. Let these amounts equal X, which is what we've done, right? Now, you have KSP is equal to X squared, which is 8.5 times 10 to the negative 17 is equal to X squared. Square root it, solve for X, and there you go. These are the concentrations at equilibrium of these guys and this guy here. That's how you do these. So with the Ka and the KSP, you need these X's. And this is a nice one because there's 1 and there's 1. 1 mole, 1 mole, 1 mole. Let's try one that is not. So here we go. Exactly the same question. I just changed the atoms and the K. Exactly the same question. So calculate the solubility of mercury bromide. And that's mercury 2 bromide, actually. And we want to know the concentrations of their ions with this KSP. And again, you look at that KSP, this thing is not dissolving well. First thing we do, bang, you do your equation. Sometimes I'll give it to you. Like instead of giving you 100 of the, giving you 100 of these where you got to make the equation and all the different, like it's a beast because you got to know all your oxidation numbers and make sure that everything adds up. And okay, this one's good. Plan this one. Make sure it's all balanced. Generally, what I'll do, if I give you a couple of these, I'll give you the chemical equation. Because there's a lot of time spent. A couple minutes anyway making this. You know, you have to refer to your periodic table and oxidation numbers and these kinds of things. But anyway, next thing we do, there we go. Now, you notice, though, when you make your chemical equation, you've got 1 mole mercury bromide, you've got 1 mole of mercury ions, but you have 2 moles of bromine. So things are a little different than the previous one. Okay, the previous one there was 1, 1, 1, easy peasy, no exponents. But now, for every mole that's produced here, I'm going to make 2 of these guys. Products over reactants. KSP is equal to this guy here times this guy here. But because there's 2 in there, okay, we got to put a square. Now, same thing, these numbers here, let mercury equal X and let bromine equal 2X. Substitute and away you go. So KSP is equal to X times 2X, and that 2X is squared. All right, that's the trick for this one. Okay, it all goes back to this step here. Willy Wonka important, crazy important. Okay, and if there's 2 moles here, there's going to be 2X here. And if there's 2 here, there's going to be a squared there, and this 2X will go inside that bracket. So eventually you're going to have X times 2X squared. And if you just doodle on a piece of paper there, 2X squared is 4X squared. Right? 2 times 2 is 4. X times X is X squared. So this right here is 4X squared. 4X squared times X is 4X cubed. Okay? So that whole thing there, and I won't go, you could get crazy on these, but I'm not. The top you'll ever get is this 4X cubed. So this right here, exam question. Okay? So now, KSP is equal to 4X cubed. Well, I gave you the KSP 1.3 times 10 to the negative 19. Okay? What do we do? Now, you're looking for X. Again, we're into the algebra. How do I get that X cubed by itself? Well, 4 times that, divide by 4 on this side, divide by 4 on that side. So I have 1.3 times 10 to the negative 19 divided by 4. Calculator, okay, and you do all the math there, and then eventually find it on your calculator. There's a cube root button, okay? That's what you'll need to solve this question, a cube root, whether it's on your computer or this or that, okay? So you divide this guy by 4, and 3.25 times 10 to the negative 20. You cube root the whole thing, and you get this answer here. Okay, so this is the concentration of this guy. What if I asked you for, and what is the concentration of this guy? It will be double 2X, right? Because this is only X. And if I asked you there, which I did, I think I asked you for the concentration of H2 plus and Br minus. This is your concentration of Hg. Double it, and you get your concentration there of 2Br. Okay? So it'd be, what, 6.4 times 10 to the negative 7. Heavy stuff. Heavy stuff. Okay?
I have a question about that one.
Yeah, good. And apologies, this is the toughest, this is the longest lecture, and I don't even know how many students are left. Might be only one, but I don't know. Okay, which one you got there? This one here?
Yeah.
All right, talk to me.
I'm just confused about how, like where it says the KSP equals Hg 2 plus and then Br minus.
Okay.
A little 2. How come you use the 2 like in front of the X layer and on the outside of the bracket.
Uh-huh.
Where does both of those twos come from?
That's the trick. Whenever you see, when you're looking at here and you make your chemical equation right here, and you'll see there that it's HBr2. Well, when these guys break up, I'm going to have double the moles of Br. Okay? That didn't happen here. Or the other one. It didn't happen. And you see, these guys here, they just broke off. If one of them breaks, there's another one here. So it's 1 to 1. So there's no exponent. Easy peasy. But with these questions here, if you get 2 moles of these guys here, which you do, well, you see, if one of these breaks, how many of these do you get? 1. If one of these breaks, how many of these do you get? 2. So you got to put 2x down here. So this is x and this is 2x here. Now you make your KSP, and this is your equation here. And whenever you have a number here, it's got to have an exponent up here. So your question is, I see it here, why is there, it's basically a double 2. And that's how you do these. So if there's a 2 out here, you put 2x here. If there's a 2 here, you got to put that exponent here. And then that 2x will go inside. So it's basically a double 2. Okay? That's how this one's done. And talk to me. Kaylee, what do you got? Anybody?
That makes more sense.
Is that okay? I know it's weird. I
Yeah.
know it's weird. But as long as you guys can, you guys are writing notes, write them till the cows come home, and make sure that whenever you see a solubility question, you're checking to see if it's 1 to 1. Like this one. Okay, 1 to 1. Yay, no exponents, no nothing, easy peasy, plug and play. But if you're doing a solubility, and you see here that, okay, so that means a double 2. That means a 2x and the squared as well. Okay? How are we doing? Anyone else? Okay, so that was your solubility there for 2 to 1. And this, we could just keep going on this. I don't know. It's a long lecture, and I apologize. But I'm telling you here, it's exactly the same as this one here. So slide 43 and 44, exactly the same. All right? I think they use S's. But you see, there's your 4s cubed. So I want you guys to go down and follow this. Here's your lead fluoride. You can read this right here. It's the same question. It's asking for the ion concentration, and it gives you the KSP. So there's your equation. And PbF2, if one of these breaks, I make 1 lead ion, but I got 2 fluoride ions. Aha, double 2 is coming. So your KSP, you make your equation. It's right here. All right. And you see here I have an S because I make 1 of these, and I have 2s. Okay, because I make 2 of those. And it's a double 2. And there's your KSP value. So here the book there, one of the books there that I use, they use S's, but you can use X's. As I said, please use a smiley face if that makes you happy. And so there's your 4s cubed, inverse cube root, and away you go, and you just solve the same way as you would there before. Okay. This question here, there is a little bit of an add-on. It was the same thing as what I did here. We solved for x, and that told us how much is here. How much of this do I have? Well, you multiply this by 2. We talked about that, and that's what this guy is here. It's asking you the last page here. This is continuing on. Should be part 2. but it just, you have to double it to find the concentration of the fluoride. It's exactly the same question as what we just did. So that's what I got. I apologize, it's way too long, but it'll free us up a week 6. We'll still have lecture week 6, but I got nothing to teach. This is where you guys can hit me. I'll give you guys a review package there, and you guys can just work away on this and kind of have a free week just to get all your thoughts in order. But other than that, I got nothing. So you guys are all free to go. I'll post this video, give me half an hour or something like that, and it'll be up on YouTube. But other than that, I got nothing. I wish you guys the best. Cheers, Hunter. Good. And so you guys are free. If you have any questions at all, stick around. If we have 3 or 4 or 10 people or whatever, it's all good, Jennifer. Cheers. If you guys have questions, let me know. Great, Ian. Great, Aisha. Thank you. And no, cheers, Kirsten. Yeah, you as well. So stick around if you have a question. If not, go and enjoy your day. Have a look at the little periodic table I gave you. Cheers, Elisa. And know those oxidation numbers. Shaylin, you're awesome. So, anyone have a question? Talk to me.
Me.
And who is me?
Alaya.
All right, very good. Okay, where are do you want me to put on screen share? Do you want me to hit a slide? Where are we?
No, I just want to ask for last week about the titration. I just want to confirm, is the unit for volume is liter the standard unit?
For the, you mean the M1, V1, M2, V2?
Correct.
Yeah.
Yes.
You can actually, for you guys there, I just keep it liters. Just keep it liters, because to be honest, you can use anything as long as it's the same on either side, and I don't want to get into that. So for you guys there, whatever volumes you're dealing with, just change it to liters, and you'll no problem at all. Because great question. I might give you milliliters and liters. Well, you can't do an M1, V1, M2, V2 if you have 2 different volume units competing. So you got to change one to the other, or change this one to that one. So keep it liters, and you'll never get a wrong answer. How's that one? Perfect. What else do you guys got? Talk to me.
I have a question about last week.
All right. The Samantha, you showed up on my screen. Samantha, what do you got? I think it was Samantha.
Yeah, sorry.
All right. Okay, we'll get back there. Samantha, what do you got?
Okay, I have just like a technical question. On slide
This week?
43. Yeah, this week.
All righty. What do you got?
I'm just having trouble getting to that answer.
I know, eh? It's a beast.
Yeah,
It is. I know. And you see, what I would do right now, actually what I do right now, I would take a half an hour, and because everyone's calculator is different. And I actually take time to show people how to use their calculator, because even sometimes I don't even know how to use them. And so are we on screen share or not?
No, not right now.
No, we're not. Okay, let me get back to screen share. And
Yeah, I was just curious if there was like a specific mode that I needed to be in to get.
Yeah, keep it in. I tried to do this as best I can. Now, what's giving you trouble? Is it the talk to me here? Where are you? Okay, you input these numbers, so you have 1.3 times 10 to the negative 9 is equal to 4x cubed. Okay. Now.
Oh, sorry.
No, go ahead. Go ahead.
Slide 42.
42. Okay.
Yeah.
Okay, same thing. Different numbers. Perfect. Now, you're able to get to here. And so we're looking for x. Well, x is tied up in a cube, and x is tied up with a 4. What's the easiest thing to get rid of? The 4. And so 4 times x, what's opposite of times? Divide. So we divide this side by 4, we divide this side by 4. And on this side here, 4 over 4 goes to 1, so it's gone. That's why we do this kind of thing. And when you 1.3 times 10 to the negative 19 divided by 4, can you get that answer? Now it's...
I'm fine with that portion. Like this question, I was able to get like the right, the exact same answer you got.
Oh, okay.
But on the other one, I only got like it's showing. It's like it's not showing as an exponent or whatever. It's just showing as like 0.00000009 or whatever. So it's like the 8 zeros and then the 9.
Okay.
So there's no 2 1 afterwards.
Is there a button on there? Sci-fi, scientific? You might want to play with it a bit. Okay. And but if you do get 0.00000027, change that back to scientific notation, because generally I won't have an answer with all those zeros. I will just convert it to 2.7 times 10 to the negative 8, and that'll be answer C. So that's how, if you're having issues with it, email me. I'm not good with calculators to begin with, but we'll try. So let me know. What else you got?
Sorry, and one more. I did email you about it. There was a question on the assignment, question number 13, on assignment 1.
I can't talk about the assignment, I'm sorry.
Oh, that's okay.
Yeah, because it's still ongoing, right?
Okay. No, yeah, there was just
what like was it though? What?
It was just a unit, like the G. Like the grams is a little g, and then there in the question there was a capital G.
It might be grams. If you tell me, can you read the question? Do you have it there, and I'll tell you. If you don't have it, you can look for it and shoot it to me.
I can probably get. Yeah, I got it. So it was, what is the percent by mass of the solution formed when 5 grams of solute is dissolved in 40 g of water?
Okay, that's grams.
Okay, perfect.
That's grams. Oh, okay, good. Woo.
Awesome. That is all I have for you. Thank you.
All right. No, it's all good. Hey, man, I love these questions, and I wish more people would stay after, because honestly, man, welcome to the hardest course you're going to take in this, and it's not physics. It's this one, and you guys are knee deep in it right now. The next after reading week, it's actually fun. I get you guys doing pictures and drawing, and it's more spatial and 3-dimensional, and but this is hardcore, man. You guys aren't going to get any worse than this. This is as tough as it's going to get it for pre-health. So you know what? I applaud you guys for coming, B, and sticking around and asking questions. Like, you know what I mean? Y'all gonna make it. I can just tell. Tell me. Who's got another question? What do you got?
I have one.
And who am I speaking to? Actually, here, I'm going to turn off the video. Just, I don't need your questions all over. What do I got here?